for those of you who are following the news, and totally understandable if you're not these days, there's a lot of focus on federal spending, and the US government is spending, and what the US government is spending money on. And whether that's a lot, or too much, or not enough, or not on the right things. And these are the questions that the right data and the right tools for interrogating these data are supposed to provide answers to. So the data journalists at New York Times, for one, are certainly hard at work trying to make it easier for the American public to understand what's going on. They've created this time series plot where the y-axis is plotted on the federal debt as a share of GDP, which makes it easier to track how much money is being spent, not just in the current moment, but since the beginning of the 20th century. And this is exactly like the kind of visualization you might make as a visualization designer, assuming that your readers know what to make of it. But data visualization literacy is a two-way street, as we've been seeing with Lily and Arvin, and it's between the designers and the viewers. And in the talk today, I'm going to be focusing on what enables viewers to understand data visualizations that the designer has created. And that understanding often starts with a question, so something the viewer wants to figure out. So for example, say you were a hotel manager in SF with an influx of peanut-loving data viz researchers on the horizon here for a workshop. How high could you get away with pricing the peanuts? So maybe you can look at the hotels in Seattle and see what they're charging, or even maybe in Las Vegas. And so say you're presented with this stacked bar chart. Unfortunately, it doesn't have armadillos, but colors will have to do. And you notice that this gives you a summary of the average snack prices in a whole bunch of cities. How would you go about completing the task of finding the cost of peanuts in Las Vegas? What information would you use? How would you go about answering my question? And so solving this task might require mapping text to this bar and the colors, as Alexa mentioned, storing different values of the red rectangle in your working memory, and performing numerical operations in your head. And from this example, we see that while data visualizations can be useful, it takes coordination of a lot of different cognitive processes to derive meaning from them, like processing visual and linguistic information and mapping it onto variables, using working memory to store where the red bar starts and ends, and even using explicit numerical operations to find the final answer. So how can we account for all of these different cognitive processes, which are needed to understand a data visualization? So while some cognitive models have been proposed, they often don't account for the diversity of data visualizations in the real world and all the different ways that we process them. So we need to build a more unified account of data visualization understanding, which can take into consideration the many different types of data visualizations and explain all the different ways that people process them. And as work of a lot of folks in computer vision, the work of Alexa and also the work of Cindy was showing, VLMs have some potential as they train on a large amount of visual data and show some promise of processing visual inputs. But can they really understand data visualizations the way humans do, as Ben was alluding to? And in this talk, I'll go over some recent work which curates some sets of assessments of data visualization literacy, and we create a procedure to evaluate vision language models on data visualizations and evaluate VLM performance compared to that of humans. So here we create a set of 6 assessments which are all made for different purposes. So some of these are designed by experts like Lily, that's there to detect misleading visualizations and cover a variety of different tasks and graph types. And we have other assessments which are either procedurally generated or created by non-experts. So while these have more items, we see that they don't have the variety in graphs and questions like the expert-created ones do. And so to evaluate these tests, we give both vision language models and humans an item, which includes a question and an image. And to find out if the models reliably give the same answer, we administer each item 10 times. And for each response, we use an LLM to extract the correct format, and then evaluate if each item has valid formatting. So for example, if the model actually responded with a multiple choice answer or just gave gibberish. And since this is literally the bare minimum standard you need to answer a question, we wanted to know how often do models even produce these valid responses? So the current vision language models we find don't always provide valid responses, and that's kind of just the best case. And we see that even other models barely provide any valid responses across tests. And even models like Matcha, which is this model picks to struct, which is fine-tuned on charts and other data visualizations, don't really provide valid responses for specifically the expert designed assessments like Colby. And even popular models like GPT-4V, which supposedly have tons of data piped through them, often struggle a lot, which we kind of find across all these models that they fail often to meet even the minimum criteria we need for evaluation. But even so, for the purposes of this study, we assume that might be resolved someday, but we try to give models the best chance possible and compare models with humans using only valid responses. And so to understand if models are as good as humans, we first attempted to see how their accuracy compares to humans across different tasks. To find out, we calculated the proportion of correct responses models gave to our questions. For tests with numerical response items, we accepted the answer to be plus or minus the 5% of the correct solution. And we see that humans perform pretty well on these expert-developed tests and chart QA. But while we see some good performance on vision language models, we see that they still underperform most humans, especially these expert-designed tests. But along what categories are they doing worse, you might be wondering. Are there some items that are just tricky for models but not tricky for humans? Are people just doing better on completely different sets of items than models? Is it the same? And to test that out, we evaluated model and human performance across a variety of different categories. So first, we grouped all the items by the different types of graphs, so like bar charts. And we also identified a common set of tasks to group the items by, like finding the value of a bar. And we compared human performance to that of the best performing model on average, so GPT-4V. And here we found that GPT-4V performs as well as humans on some graphs and tasks, but severely underperforms compared to humans on others, like stacked bar charts, for example. And this suggests that model performance doesn't always align with human performance across all these different categories of items. And so what happens if we zoom in even further? Does this happen at the item level? How do models compare to humans across individual items themselves? To explore this, we compared the accuracy across each of the test items between both models and humans. And we noticed that the models that achieved similar performance didn't make similar errors, and most were only somewhat correlated with humans. But they were nowhere near as aligned with humans as humans were amongst themselves. So here, the human noise ceiling shows how different groups of human participants are correlated with one another. So we can really see that these models actually don't produce human-like error patterns just yet. So to recap, our work introduces a suite of 6 assessments and uses them to evaluate if recently developed vision language models behave similarly to human participants. And while vision language models show some promise of assisting with the development of cognitive models of data visualization understanding, additional work is really needed in order to explore the behavioral gaps between VLMs and humans. And one direction here is to create better measures of data visualization literacy, which evaluate a diverse range of skills. So to do so, we first need to understand what skills different assessments even measure. So in some work led by Eric Brockbank in collaboration with LACE, we've tried to evaluate whether 2 assessments in this evaluation set, GGR and VLAT, even are talking about the same set of skills. Do they test different sets of skills? And in another line of work that I want to shout out, Judy and I have also looked into what factors give rise to differences in behavior across these assessments. So for example, why might some people find one item easy but another so difficult? And these are both across many of the assessments that I've been mentioning today. So with that, I will wrap up and just want to give a big shout out to all my collaborators, Chris, Elisa, Judy, and the rest of my Thank you.
All right, we have time for questions.
So I don't know if you know his work, but Marcel Binz and various other people have this Centaur data set where they're trying to train LLMs on human-like responses. So I'm just curious about whether you think there could be something analogous to that, where you have the human-like responses, whether they're right or wrong, but you're trying to train the systems to fit those?
Yeah, I mean, I think that particular work, right, I think is just language based. But yeah, in theory, we could have like a data set of human experiments that are specific to data visualizations and try to fine tune models across these. But yeah, okay. But I think in one of our models, Matcha, which it does consist of a lot of question or is fine-tuned on charts. I think the performance was not improved that significantly. I think it'd be an interesting case study to try, but definitely like look into whether give it like fine-tuning models on like human responses would be interesting, but definitely looking at like Matcha and other models which have been already fine-tuned on charts still has not provided like promising results.
Other questions? Yes, here you go.
Yeah, maybe a little bit follow up on that fine-tune questions.
Yeah.
As you mentioned, Matcha is a relatively like small model.
Yeah.
So I think it's kind of like complementary with the GPT-4, which is larger models. If you can fine-tune on the data sets that Matcha uses, it could be interesting to look at if that would even improve the performance of producing some reasonable output.
Yeah, definitely.
All right, let's thank Arnav once again.